All right, you can all read, hopefully, Differential Topology. In the 1960s, a man by the name of John W. Milner put on an incredible lecture series which we're all still fortunate enough to have access to today. You can search it up here on YouTube, look up Differential Topology. It should be one of the first videos you see. Altogether, there are 3 parts making up 3 hours of an incredibly informative talk on the subject. But as he even says in the talk, he isn't able to get to anything and to everything in the subject of differential topology in 3 hours. There's simply too much of the subject. So while my predecessor of 60 years was far more a master of the subject than I and much greater a lecturer than I could hope to be at this point, I would like to take advantage of something he didn't have at his moment of creating his lecture series, which is time. I can make this as long as I want. So what I would like to do to follow up his great work is to create an incredibly detailed exposition of the subject, starting from the wholly abstract definitions and defining properly all the objects in play and coming upon some of the greater theorems of the subject that really give it its character and, as Milner said at the time, distinguish it from the other forms of topology. So, in order to follow along with my exposition, you're going to need to be fairly acquainted with set theory, also multivariable analysis, so analysis in several real variables. We won't be requiring complex analysis. You'll also need to understand linear algebra, obviously, as you would to understand the calculus of several real variables, and abstract algebra. As for when we touch on subjects like de Rham cohomology, having no understanding of groups would render the entire thing quite meaningless. So, but altogether, just set theory, linear algebra, abstract algebra, and multivariable analysis, and general topology, excuse me, almost forgot, general topology, right here in the name, topology. Knowing all those together, particularly the properties of topological manifolds, which I'll be leaning on rather heavily, you should be prepared adequately to follow what I'm going to be talking about. So now that without talking your ear off more about the subject and why I'm doing this, let's get on to our primary motivating definitions, the objects that are smooth manifolds and the functions between them that we are interested in, called smooth maps. So in order to define a smooth manifold, I'm going to need to define several other ancillary objects that I'll need in order to actually fully capture what I'm talking about here. And the first one is a smooth atlas. So recall quickly that an atlas on a topological manifold is a set of pairs, and these pairs contain, the first element is an open set on the manifold, and the second element is a homeomorphism from this open set into n-dimensional Euclidean space. So it's a function into a Euclidean space which is homeomorphic. And for every, and now these charts, which are what these pairs of open sets and functions from these open sets into Euclidean space are called, the collection of open sets must cover the entire manifold so that every point has a chart somewhere that sends it into Euclidean space. And that's what this collection of charts is in an atlas. So just to recall what one of these things is, or what these things are, rather. And so one of these atlases on a manifold M is called smooth if all chart transitions, these guys, are smooth. And let me explain what these guys are. So remember, there are elements in A, and they look like an open set U and a function x from U into Euclidean space. So if I took any two pairs, so a U alpha, x alpha, and a U beta, x beta, then there's a transition function that happens when I go from the Euclidean space that is the range of one of my chart transitions to the Euclidean space that is the range of my other chart transition, governed by this sort of composition, the composition of one with the inverse of another, so that this thing takes in an object in Euclidean space and sends an object back into Euclidean space. So this is just a function from Rn to Rm. It's a function in Euclidean space. So from real analysis, we know how to take derivatives of this sort of object and ask if this sort of thing is differentiable. So I'm going to say that an atlas is smooth if every single one of these functions, which we know how to analyze, is also smooth in the sense that you're familiar with. That is, all partial derivatives of all orders existing and being continuous. So if this occurs, I have one of these atlases, and any chart transition that I form like this is in fact smooth, then I will call the atlas itself a smooth atlas. So these are going to be necessary in order to define actual differentiation on a smooth manifold. So but before we deal with actually defining differentiation, we have to deal with a problem that we dealt with when we have to deal with the same sort of problem that we deal with when we're parameterizing curves, for example. There is no unique parameterization for even a line, for example. You could traverse it at a number of different speeds, and all of these parameterizations are equally valid. Just as well, you could have lots of different smooth atlases for one manifold, and there's no canonical choice that we've established yet. So let's work a little bit harder to finding out what choice of atlas we should actually be going with. So that's what I'll be working up to next. Before we move too swiftly on, I realized that I wrote down that definition a bit too quickly, and I forgot something. So these chart transitions, like I wrote down a second ago, they're required to be smooth only if these open sets that the chart transitions are, the charts themselves are mapping from the manifold into Euclidean space. If these intersections are non-empty, then this chart transition is required to be smooth. But I am saying nothing about those which have empty intersections. Those are, I don't care about. All right, so now having access to the concept of a smooth atlas and knowing that we need to find perhaps the right smooth atlas to talk about, I would like to use that as motivation for this relation that I'm about to define on charts and smooth atlases. And that is that a smooth atlas A here is compatible with another smooth atlas A2, or A1 rather, is compatible with another smooth atlas A2, if their union, A1 union A2, is also a smooth atlas. So every chart transition contained in it is smooth. So, and then also a single chart, the pair U and X, is compatible with a smooth atlas A if the union of the singleton set containing that chart and A is also a smooth atlas. So I'll actually go through it and prove here in a second, but this notion of compatibility here when I express it on smooth atlases in particular is actually an equivalence relation. And its equivalence classes, the equivalence classes of smooth atlases on a manifold, will contain each that canonical choice of smooth atlas that I was hinting at before. And this definition here of just having a chart being compatible to a whole smooth atlas will be very useful in the coming proofs to deal with this. So now we'll move on to our first proposition. And what I'd like to do is connect those two different types of compatibilities, the ones between smooth atlases and between charts and smooth atlases, to show that there are actually two expressions of the exact same thing. A smooth atlas A1 is compatible with a smooth atlas A2, which is what I mean by this little squiggle symbol here, if and only if, for every chart contained in my smooth atlas A1, the first one, that chart is also compatible with A2. So every chart in my first smooth atlas is compatible with my second smooth atlas if A1 is compatible with A2. That's the first thing that I'd like to prove for you. And it should, hopefully, just by the definition that I gave you last, it should be kind of apparent as to why this is going to work out. But nonetheless, it's our job as mathematicians to clearly prove out everything that we do. That is one of the modern standards of rigor that we are to hold ourselves to. So this is no exception, regardless of how obvious it might seem going into it. I'm going to lay out a fully fledged argument for it. So I will be proving this biconditional statement by contradiction both ways. So assume instead that A1 was in fact compatible with the smooth atlas A2, but on the contrary, that there also existed a chart UX in A1 so that UX was not compatible with A2. So having these two assumptions, I'll be able to break one of my previous definitions and show that this derives a contradiction. Meaning, if I assume that A1 is compatible with A2, then I can't have the existence of a set such as this. So that's what will follow after I've erased this board and moved on to the next part. All right, so if our chart UX isn't compatible with A2, then by the definition that I gave you a second ago, that means that the union of the singleton of that chart with the smooth atlas A2 is not itself a smooth atlas. So negating our definition of smooth atlas, this means that there has to exist a chart pair in this set here such that their transition, which I gave you in the definition of a smooth atlas, that transition function isn't smooth. Now our smooth atlas A2, it's defined to be a smooth atlas. So every single choice of function pairs in A2 alone has to have a smooth transition. Thus, only one element in the pair coming from our set of the union up here, only one element of the pair that has this non-smooth transition can come from A2. Because if both elements, both charts came from A2, then because A2 is a smooth atlas, their transition would also have to be smooth. Since there's only one other choice for what the chart that's causing the problem could be, this leads us to the obvious conclusion that there has to exist some function, or not just a function, but some chart in our smooth atlas A2 such that the transition with this new, not compatible chart isn't smooth. So I'll write that down on the next, but that's what we figured out here. So because this fails to be a smooth atlas, there must be a non-smooth chart transition. There can't be a non-smooth chart transition contained entirely in here, so it must be that the non-smooth chart transition occurs with this object combined with some object contained in A2. All right, so then there exists some chart in A2, in our smooth atlas A2, such that V and U have a non-empty intersection, and this transition function, y compose x inverse, which goes from the range of x, that non-empty intersection, to the range of y, that non-empty intersection. This guy isn't a smooth map. But recall that we began this proof by assuming that A1 was compatible with A2, meaning that the set A1 union A2 is a smooth atlas. Well, if A1 union A2 is a smooth atlas, then all charts contained in it must have smooth chart transitions for any function pair, chart pair that I choose. However, this one, as we just concluded, it must not be smooth. But both of these charts exist in the union because this first chart exists in A1. That's how we defined it. It was a chart from A1, which was not compatible with A2. And the second chart, Vy, we got from A2. Since both of these charts belonged in the union constituents of our final set, they both belong in the union. Meaning that this chart transition is one of the chart transitions of this set. So this set can't be a smooth atlas. A contradiction. So we're forced to drop our contradictory assumption. If it is that A1 is compatible with A2, then every chart contained within A1 must be compatible with A2, otherwise this contradiction would ensue. So this handles the first half of our biconditional statement. All right, so now moving on to proving the second half of our biconditional statement, I'm also going to be doing this one by contradiction. And it's going to turn out looking very similar. So this time we're going to assume that For any choice of chart, UX, contained in my first smooth atlas A1, the chart UX is in fact compatible with my smooth atlas A2. And that my first smooth atlas A1 is not compatible with my second smooth atlas A2. So everything in A1 is compatible with A2, but the smooth atlas itself is not. And I'm going to show that this would also bring about a contradiction. So just as before, I'm going to use the definition of compatibility here. I'm going to invert it to see that if this smooth atlas is not compatible with that smooth atlas, it means that their union, A1 union A2, is not a smooth atlas. Remembering that the definition of smooth atlas meant that any two functions, or any two charts rather, which had overlapping regions with a non-empty intersection, they had to have a smooth chart transition. So if you're not a smooth atlas, then you have some pair of charts which have a non-empty intersection and have a non-smooth chart transition, which is exactly what I've written here. This is exactly what this not being a smooth atlas means. So we're guaranteed the existence of at least one non-smooth pair of, one pair of charts with a non-smooth transition function and overlapping domains. Furthermore, I haven't written this down, but this part you'll just have to follow me here. Furthermore, the smooth atlas A1 and the smooth atlas A2 are both smooth atlases themselves. So if I chose two charts in A1, they couldn't have a non-smooth transition map if their intersection wasn't empty, because this is a smooth atlas, and then it would contradict the definition of smooth atlas. Likewise for A2. So if I'm to choose a pair of charts from the union of A1 and A2, such that their domains overlap, they have a non-empty intersection, and the chart transitions are smooth, then I'm going to need to take one of these charts from A1 and one of these charts from A2, because once again, it won't work if I take it from both. They won't have a non-smooth chart. They won't have a non-smooth transition and a non-empty intersection. So after all that long discussion there, we know that there exists some chart in A1 and some chart in A2, such that their domains have a non-empty intersection, and the chart transition is non-smooth. So I'll write that up as our findings, and then we'll see where that takes us. All right, so we found that there exists a chart in A1 and a chart in A2, so that they have a non-empty intersection of their domains, and that the transition map given by this composition here isn't a smooth function. But that's a problem, because we assumed in the very beginning that every single chart contained in A was compatible with A2, so that every single union of a chart with a singleton containing only a chart from A1 and the set A2 had to be a smooth atlas by the definition of compatibility. However, this set of charts can't be a smooth atlas by our reasoning, because this function here isn't smooth, and he must certainly be one of the transition maps contained in this atlas, because this chart is contained in A2, and this chart is exactly the chart that we've adjoined onto that set. So this is not a smooth atlas, meaning this chart, rather, is not compatible with this smooth atlas A2, which contradicts our assumption from the very beginning. So what we've learned now from the contradiction we've discovered is that if we assume that every single chart contained in A is actually compatible with A2, with our other smooth atlas, then it has to be that both of the atlases themselves are compatible, otherwise we would find this contradiction here. So that proves both directions of this proposition, and now we can use it willy-nilly as sort of a test. This will be a useful tool in several arguments that I'm going to make, because now I can transfer straight from saying that two atlases are compatible to saying that every chart in the first atlas is compatible with the second atlas, And once I've shown you that this atlas compatibility is actually, in fact, an equivalence relation, then I don't actually have to make a distinction between front and backwards anymore, and we can just say two smooth atlases are compatible, as opposed to a smooth atlas one is compatible with a second smooth atlas, the way we have to say it right now. But that's what's coming next. So this is our first proposition proved. On to the next. All right. So in order to have that equivalence relation proof for compatibility, I'm going to need several other ancillary definitions and propositions. Otherwise, the argument would be fairly long. And one of the ways you can tell that you are proceeding in a proper at a proper pace theoretically is if your arguments are short and rather intuitive. So on with more definitions and propositions. A smooth atlas S is called a smooth structure. So not just a smooth atlas, but a smooth structure if for any atlas A, for which A is compatible with S, A happens to be contained in S as well. So any atlas which is compatible with S has to be contained in S in order for S to be a smooth structure. So in some way, it's like the biggest smooth atlas of all the compatible charts that you can make with this set, because there will be more than one smooth atlas, and not all of them will be the same, and lots of them will be smaller than the smooth structure, but all of them will belong to this same smooth structure, and as I'll show you soon, that will mean they'll all have to be compatible with one another. And this will be actually a key part in my argument about the equivalence relation. So this is a smooth structure, and this is in fact actually that canonical choice of smooth atlas that I was mentioning towards the beginning. Because we've taken him to be maximal in the sense of set containment, he's actually unique in a way that our previous atlases weren't. This smooth structure, as we'll come to find, is uniquely determined by the equivalence class of the smooth atlases that it contains. And so currently, that's just me making a claim, but I will now demonstrate that over a few other after a few other definitions and propositions. So that's what we're working towards now. So here's our second proposition. If I give you two smooth structures, S0 and S1, and you know that one of them, say S0, is contained in S1, the other smooth structure, then in fact, both of these smooth structures are in fact equal. So let me demonstrate that. Let's go ahead and assume that we're given two smooth structures, S0 and S1, and that we know that S0 is in fact contained in S1. So we know this. Well, if this is true, then S0 union S1 is just equal to S1, because S0 is contained inside of S1. We're not adding any new elements. But we know that S1 is a smooth atlas, because it's a smooth structure, and a smooth structure is defined to be a particular smooth atlas. Thus, by our definition, these two are compatible. In fact, actually, I'm going to flip it around because I don't need this to be compatible with this. I need this to be compatible with this. But let me show you that we actually have that, because this union is the same as this union. And now they're in the correct order for me to use my definition. Once again, I haven't actually proven that it's an equivalence relation yet, so I can't just swap it back and forth symmetrically as much as I'd like to, and I know that it would work. I need to demonstrate it, otherwise I'm producing a circular argument, and that is no bueno. Okay, so this union is in fact a smooth atlas, so that means this is compatible with this. But recall the definition of smooth structure. S0 is a smooth structure because whenever a smooth atlas, say S1, is compatible with S0, well, it is in fact contained inside of S0. That's what it means to be a smooth atlas. But with this containment and the reverse containment, we get exactly that the two smooth structures are equal. So this is a nice and short one, and it's fairly easy to understand. These objects are supposed to be maximal, so if one's in another, they have to be the same. And that's essentially how the argument went as well. So now we have this, we'll move on to our third proposition. So now moving quickly on to proposition 3, I'd like to convince you that if two smooth atlases A1 and A2 are contained in a third smooth atlas, just A, then in fact A1 is compatible with A2. And here's how I'm going to demonstrate that. Assuming that this is the case, that both smooth atlases A1 and A2 are contained in my third smooth atlas A, then for certain the union of these two smooth atlases is contained in it. And then we can quickly see that if this union was not a smooth atlas, that would mean that it contained two charts that had a non-empty intersecting domain, a domain with intersection that was non-empty, and for which the chart transition was no longer a smooth function. So if this set contains such a pair, then because it's contained in A must also contain that pair of charts. So then A must also fail to be a smooth atlas, which is a contradiction. We assumed A to be a smooth atlas in the beginning. So in order to avoid this contradiction, we have to drop the assumption that this union contained a pair of charts that didn't have a smooth intersection, a smooth transition, but had also a non-empty intersection. So that means that this can't happen. Every single chart pair in this guy has to be either empty at the domain intersection level, or non-empty, and the transition maps are all smooth. So that completes the proof, because that is exactly what it means for this object to be compatible with this object by the definition that I gave you. So that's proposition 3 proved. So if any two smooth atlases are contained in a third one, we know automatically that this first one is contained in the second one, and then obviously this can be swapped around, so you could easily get symmetry from this, but I'll wait until we get to the actual equivalence class proof, because I'm just going to tackle it all at once. So there's proposition 3. On to the next. Now to proposition 4. This is a slightly longer one, but it's a really important fact. Every single smooth atlas is contained in a unique, that is a single smooth structure. So there's several parts to this proof, which is why it's going to be a little longer than the one I just did. So I need to show you that every smooth atlas is contained in some larger set of charts. I need to show that that larger set of charts is in fact a smooth atlas. I need to show that that smooth atlas is in fact a smooth structure, and then I need to show that that smooth structure is in fact unique. So there's 4 parts to this proof, and I will be breaking it up into all 4 parts so that it'll be much easier to follow along. And I'm going to start off with just constructing this set that is eventually going to be the smooth structure. But right now, we're just going to be sure that it is a set of charts that contains our smooth atlas, whatever it is. So let A, just capital A here, be some smooth atlas, and I'm going to define into existence this set S, which is the set of all charts such that this chart is compatible with our set A. So it's all of those charts amassed into one, and I'm going to be showing you that this guy is in fact a smooth structure. But first, we need to find out whether or not A actually lives in there itself. So that's the first part of my argument, which we'll be getting to right now. All right, on with the proof. You can see I'm shaved and wearing a different shirt, so this is continuing on a different day. But our ideas are still the same. I'm still talking about that same set S that I just defined, and now I want to show that my smooth atlas A is in fact contained in it. So here's how I'm going to do that. Let this chart here, UX, be contained in my smooth atlas. So any one of these guys, which is what this for all symbol here is saying, for any one of these guys such that he's actually contained in my atlas, then the union of the singleton of that chart with that atlas is again just that atlas, because this chart is contained inside of this atlas, so I'm not adding anything new. Now, this atlas is a smooth atlas by definition, so by the definition that I gave you a long time ago, this chart is compatible with that smooth atlas there. That means, by the definition of S that we just gave, that every smooth chart that's contained in A, like this, also has to be contained in S, because it's compatible with A. And that's how we defined S into existence. S is all of the charts that are compatible with A. So then, because any chart contained in A is compatible with itself, it must also be in S, and therefore, since every chart in A is in S, A is a subset of S, because these are just sets of charts. Alright, so we've got the first part. We know that this set S that I've given you of all the charts that are compatible with A does in fact contain A, because every chart in A is compatible with itself. Alright, so we've just found out that our smooth atlas A is in fact contained in this set S that I've defined. So, in the very least, all of the charts in A cover whatever manifold these atlases are supposed to be on. So, since every chart in A is contained in S, what's meant by being a subset, this means that the charts in S have to cover the same manifold that A covers, because A represents a cover of that manifold, and the charts in A are a subset of all possible charts in S. So they must at least still cover the same space. So knowing that every single point on our manifold actually has a chart that belongs in S that covers or that contains it, that is one of the constituents of being an atlas. An atlas, first of all, has to make sure that every single domain, or that every single point on our manifold is contained in at least one domain of a chart. So that's necessary to be an atlas, and this is the first part of it. We know for a fact that S actually does cover our manifold. So now we need to check the smooth component of this, because if the definition of atlas requires that the chart transitions of different functions also be continuous. However, anything that's smooth is automatically continuous, so we don't need to cover that step. Now that we've shown that S in fact covers M, we simply just need to show that all chart transitions contained in S are smooth, and then we will be finished showing that S is a smooth atlas. So let's move on to that. So let UX and WY be two choices of chart in S. And remember that if we're in S, it means that we're compatible with A. That's how we defined S into existence. S is all the charts which are compatible with A. So in particular, these two charts here are compatible with A. And let's pick those charts so that their intersection isn't empty. It contains something. A is an atlas, by our definition in the first part. So because it's an atlas, for any point on our manifold, in particular any point contained in this non-empty intersection, there has to exist some chart, VZ, so that that point is in V, because an atlas like A covers a manifold, and P is on our manifold. And moreover, because V contains P, this means that the intersection V intersect U intersect W is also not empty. And in fact, since we know topology, and this is the finite union of open sets, or finite intersection rather of open sets, it is actually an open set that contains P. This is in fact a neighborhood of P. But so we know we have this non-empty neighborhood of P, and now I'm going to show you that we can use this chart here to prove that these two charts must have a smooth chart transition. So that's what's coming up next. All right, so we know that three-way intersection of open sets V, W, and U is not empty. And this actually gives us two other important facts. We know now that the intersection between W and V is not empty, because if it were empty, the intersection with an empty set is always the empty set. So that wouldn't happen. Likewise, the intersection of U and V also is non-empty. And recall that since the charts ux and wy existed in S, they are members of S, that's how we picked them, they're compatible with A, because that's how we defined all of the objects in S into existence. Or rather, that's how we defined S itself into existence. The objects were already there as far as we know. Alrighty, so by the definition of compatibility, this means that these two unions, the union of the singleton ux with A and the union of the singleton wy with A, these must both be smooth atlases. So in particular, every chart transition that we can find in these two sets must be smooth. Well, excellent. We remember that this chart, VZ, was in A. That's how we picked it. In particular, V contained P. Well, because these two intersections are non-empty, U intersect V and W intersect V are non-empty, and this chart and UX is in this union, and this chart and WY is in that union, it means that the chart transitions between VZ and those two charts must be smooth. It has to be, because that's what we require from a smooth atlas, that whenever those intersections are non-empty, these chart transitions are smooth. I'm sure you can already see where this is going. Just by composing these two chart transitions together, we are going to get the chart transition from X, the chart transition X compose Y inverse. But we're not going to be getting it on all of U intersect W. We're only going to be getting it on V intersect U intersect W. So you might think to yourself, gosh, we're not getting the smoothness that we need in order to show this as a smooth atlas. But recall that I chose P in the non-empty intersection of W and U to be any point. That means for any point contained in the intersection, where is it? U intersect W, for anyone in just that set, there is one of these intersections, an intersection with another open set, such that it's contained in there, and by our reasoning, the transition map that's defined on that intersection must be smooth. So we can patch together all of these transition maps because they cover every single point in our domain, every point yp in our domain, because p could be any point in the non-empty intersection of there. And I'll show you in a second, we can patch all these functions together to get a chart transition from the range of y under U intersect W to the range of X under U intersect W, which will be exactly what we need to show that all chart transitions are smooth. Because recall, X and Y are arbitrarily chosen maps, coordinate maps, from our set S. So we're very, very close to showing that this set S is in fact a smooth atlas. So let me erase this and get on to the next part. All right, so making precise those heuristics that I just gave, I can in fact compose those two functions because this one begins at Z evaluated at this set, and this one lands in Z evaluated at this set. So I can in fact compose them, and what I get is the composition of X composed with Y inverse, but restricted to the range of Y under this intersection. So not this, which is what we would need in order to, and in fact it wouldn't be the restriction anymore, but not this, which is what we need to show as smooth in order for our set S to actually be a smooth atlas. But recall, from that argument that we just posed, for any point yp in Y, because we started with any point P existing in this intersection, we know that there's some chart so that we can create this restriction, and yp is one of the points in here. So yeah, yp is one of the points in this restriction, and this restriction is a smooth map. Now, I'm not sure if you recall, but I really hope you do, because I asked you to remember your multivariable calculus. If I have a function, and for every point I can find an open set such the restriction of that function to that open set is smooth, then the entire function must indeed be smooth. So this whole function, x compose y inverse, must be smooth on its entire domain, which is exactly what we needed because remember, x and y were two charts, or two coordinate maps rather, that we chose from two charts which were arbitrarily picked out of our set S so that their intersection was not empty. And now we've shown that their transition map is smooth, so therefore S must in fact be a smooth atlas. So we're done with two of the four parts of this proof. So now on to part 3, which will be much faster due to all of the work we've spent proving the previous propositions that we have. So we're trying to prove now that S is a smooth structure because we know it contains A, and we know it is in fact a smooth atlas. So we now have to show that any smooth atlas rather, that is compatible with S must also be contained in it. So let B be a smooth atlas so that B is compatible with S. Then we know that B union S is a smooth atlas. And furthermore, because A is in S and B is a subset of itself, we know that A and B are both subsets of the union B union S, which again is a smooth atlas. By proposition 3, we proved that any two smooth atlases that are contained in a third smooth atlas must be compatible. So then we know that A is compatible with B. And then by proposition 1, we know that if two smooth atlases are compatible, every chart contained in the first smooth atlas is compatible with the second one. So, just to realign ourselves with our definition, we know that if so there, now it's going the correct direction. If B is compatible with A, then by proposition 1, every chart contained in B has to be compatible with A. There we have the correct directions, and I'm not implicitly using symmetry, which I haven't proved yet. So I'm getting to it. It'll be a lot faster to do it all together after I've done all this, I promise. All right, so we know that if this chart is contained in B, then it must be compatible with A by proposition 1. And by our definition of S, if you're compatible with A, you must live in S. So, since this was true for any chart contained in B, any chart contained in B must also be contained in S, then by definition, B is a subset of S, which gives us our smooth structure requirement. Any smooth atlas B, which is compatible with S, by this reasoning, must be contained in it. So it is, in fact, a smooth structure, and that leaves us with our final part of the proof. I got to show you that this S that I've made is the only S that is built this way. If I constructed a second smooth structure that contained an atlas, then those two smooth structures would have to be the same. So that's what I'm going to justify to you now. So now we're in the home stretch. So I need to show you that this smooth structure S that I have constructed, I've shown that it contains A, it is a smooth atlas, and furthermore, actually a smooth structure. Now I need to show you that it is the only smooth structure that contains A. So let S0 and S1 be two smooth structures so that A is contained in both of them. It's contained in S0 and it's contained in S1. Then we know that both A and S0 are contained in S0, and both A and S1 are contained in S1. So by proposition 3 rather, this means that S1 is compatible with A and S0 is compatible with A because these two atlases are contained in a third smooth atlas, and likewise over here. And then by proposition 1, we know that if two smooth atlases are compatible, then every chart in the first one is compatible with the second one. So thus, every chart that is in either S1 or in S0 must be compatible with A. So if you're in S1 or in S0, then you have to be, and so that looked like a little 1 there, that was the same S we've been working with the whole time, that S that I defined into existence, which is all of the smooth charts, that is all of the charts that are compatible with A. So now we know that if these charts are contained in our smooth structures S1 and S0, they must be compatible with A, so they must be in that original smooth structure. And since that was true for every chart that we chose from S1 or from S2, it means that both S0 and S1 are contained in our original smooth structure S. But recall proposition 2, which said that if I ever had two smooth structures and one of them was a subset of the other, then these two smooth structures must be equal. So having these subset equalities, or subset relations here, tells me that all three of these have to be equal, because S1 must be equal to S, and S0 must be equal to S, and by the transitive property of equality, S0 must be then equal to S1. So that for any two smooth structures that contain A, they must be the same, otherwise known as uniqueness. There is only one smooth structure containing any smooth atlas A, and that's proposition 4. And it will be coming up quite a couple times, but this smooth structure, this unique one, is what's going to help us define a canonical smooth manifold that has a particular correct choice of atlas, but at the same time, because any atlas determines a single smooth structure, and there are lots of smooth atlases contained in a smooth structure, you can just pick a smooth atlas from a smooth structure that's nice and small and simple enough for you to use, with the understanding that it generates that entire smooth structure, and that's the actual manifold you're talking about. So once again, that's a little heuristic. I'll make that more precise later, but for now, we have proposition 4. Every smooth atlas is contained in a unique smooth structure. All right, we're drawing closer and closer to actually defining smooth manifolds. So now I want you to believe that if I have two smooth atlases, A0 and A1, and in fact, if A0 is compatible with A1, A0 is compatible with A1 if and only if A0 and A1 are contained in the same smooth structure. So compatibility requires that both charts, or both smooth atlases rather, I keep confusing them with charts, both of them end up living in the exact same smooth structure. So let me justify that for you. So assume that A0 was compatible with A1, just by that second definition that I gave you so long ago for me, but not too long ago for you. And so that by that definition, the union of A0, A1 is in fact a smooth atlas. Then we know from the proposition 4 that we just proved, since A0, A1 is a smooth atlas, there exists a unique, which is what this little exclamation point here means, unique. There exists a unique smooth structure S, so that the union of A0, A1 is contained in S. But if the union of A0 and A1 is contained in S, then A0 is contained in S, and A1 is contained in S, which is exactly the first direction of our proof. If these things are compatible, then they're both contained in the same unique smooth structure. Okay, so there's the first half of our proof. I'll wipe this down and get to the second. All right, and now for the second, much shorter half of our proof. Let's just assume that the smooth atlases A0 and A1 are contained in a smooth structure S. Then remember, a smooth structure is in fact a smooth atlas, and by proposition 3, if two smooth atlases are contained in a third smooth atlas, then those first two, in fact, the first one must be compatible with the second one. And since the ordering here it doesn't matter, you could use either order. That's the way the definition was set up. So because you can swap either side of a parentheses, that's obviously commutative. Okay, so this settles prop 5. Now I know that compatibility is equivalent to living in the same smooth structure. This smooth structure, we'll find out, is actually kind of like, it is the largest member of the equivalence class, which is generated by this equivalence relation, compatibility, that I've been throwing around. So this is one aspect of that, and once I have, with this, and I think I two more propositions, I'll be able to actually go forward with the equivalence relation proof. Okay, so now here's our last proposition before I go ahead and prove the theorem that this relation of atlas compatibility is in fact an equivalence relation on smooth atlases. So this proposition is going to be that if I have A, some smooth atlas, contained inside the intersection of two other smooth atlases, A0 and A1, then it has to be that A0 is compatible with A1. And let's see why. So if A is defined to be some smooth atlas contained inside the intersection of A0 and A1, then clearly A and A0 are both contained in A0, and A and A1 are both contained in A1. Therefore, by proposition 3, A is compatible with A1 and A is compatible with A0. And this means by proposition 5, which we just proved, that A0 and A1 are contained in the same smooth structure S0, while A and A1 are contained in the same smooth structure S1. But by proposition 4, we know that A being inside of two smooth structures S0 and S1 implies that S0 has to be equal to S1 because the smooth structure containing any smooth atlas is unique. Now, if S0 is equal to S1, then we have that A0 is in this smooth structure, and A1 is also in this smooth structure. So by a repeated application of proposition 5, because these two smooth atlases lie in the same smooth structure, they must be compatible. So we have that A0 is compatible with A1. And with this proposition here, I'll have everything that I need to very quickly prove that this atlas compatibility is in fact an equivalence relation. All right, so now the theorem that I've been teasing this entire time. Atlas compatibility is in fact an equivalence relation, and it's going to be pretty quick to see, at least for these first two ones, but all of those propositions that I spent this time proving will make even the third part, transitivity, quite simple to show as well. All right, so first of all, I'm going to show you that this relation, atlas compatibility, is reflexive, meaning that anything is compatible with itself. So, note that the union of a smooth atlas A with itself is just itself again, which is in fact a smooth atlas. So by the definition of compatibility, a smooth atlas must be compatible with itself, because its union with itself is a smooth atlas. Now, if A0, a smooth atlas, was compatible with a smooth atlas A1, then that meant that A0 union A1 was a smooth atlas. However, unions are commutative. It doesn't matter which order that I union things together in, I get the same set. So in fact, if this set is a smooth atlas, this set is also a smooth atlas, which by definition tells us that A1 is compatible with A0. So our relationship is symmetric, which is something that I've been catching myself from saying and using throughout the proofs that I have been showing so far, because I can't use them before I've shown this. But as you can see, that part wasn't really hard. The only part where our propositions are going to come in here is actually during transitivity. Now we're going to talk about transitivity. So what transitivity means generally is that if I have A related to B and B related to C, then A has to also be related to C. So let's see that that works out here. So let's let A0, a smooth atlas A0, be compatible with a smooth atlas A1, and a smooth atlas A1 be compatible with a smooth atlas A2. So by definition, that means that this union over here, A0 union A1, and this union over here, A1 union A2, these are both smooth atlases. Alrighty. So, and I'll see how that helps us once I've wiped this board down. Alright, so knowing that both of those sets, A0 union 1 and A1 union 2, A2 rather, are smooth atlases, and knowing that both A1 is a member of both of these unions, means that A1 is going to be a subset of the intersection of these two smooth atlases. And since A1 is a smooth atlas, we know that these two smooth atlases intersect in a set that contains a smooth atlas, and therefore, by the proposition that we just proved, proposition 6, we get that these two sets, A0 union A1, and we get that this set is compatible with this set, which we know is the same thing. It's just saying they're both compatible by symmetry. It doesn't matter which order we do at this point. So knowing that these two sets are compatible, or these two smooth atlases are compatible, means that their union, which can be written like this because both of these unions contain A1, is in fact a smooth atlas. But then this union, because A0 and A2 are members of the union, this union contains A0 and A2. So A0 and A2, two smooth atlases, are contained in a third smooth atlas, and therefore by proposition 3, they must be compatible as well. And that covers transitivity, because now if A0 is compatible with A1 and A1 is compatible with A2, it must mean that A0 and A2 are compatible. And so this relation of smooth atlas compatibility on smooth atlases has all of the necessary properties, reflexivity, symmetry, and transitivity, in order to be an equivalence relation on these smooth atlases. All right, so this is now a corollary to that theorem, but it'll be, as it's a corollary, it's going to be quite short. So every equivalence class of smooth atlases contains a unique smooth structure. All right, so let E be an equivalence class of all the smooth atlases, rather. So by an equivalence class, it means that every object in there is equivalent, and it is all of the objects which are equivalent to some particular chosen one. So you choose, say, a particular smooth atlas A, and then ask what are all of the sets equivalent to that A, and that's how you generate an equivalence class represented by A. But here, I don't care about the representation. All I care about is the fact that it's an equivalence class. Everything in it is equivalent in terms of smooth atlas compatibility. So let S0 and S1 be two smooth structures that are contained inside of this equivalence class. Remember, I want to show that these things are unique, so I have to show that given any two smooth structures, they have to actually be the same if they're contained in my equivalence class. But remember, if you are contained in my equivalence class, like I said, that means that you are equivalent by the relation that I told you, which is atlas compatibility. So the smooth atlas S0, because the smooth structure is a smooth atlas, is compatible with the smooth atlas S1. So then, by proposition 5, they both have to be contained in the same smooth structure, say S. But by proposition 2, which I proved a long time ago, anytime two smooth structures are, anytime one smooth structure is contained in a second smooth structure, then those two smooth structures must be equal. So having these two smooth structures contained in this one means that I can draw equality between all three of them, which tells me that S0 is in fact equal to S1 by the transitive property of equality. And therefore, there is in fact only one smooth structure per equivalence class, which is what I set out to claim, which is what I claimed and then set out to prove. So here we are, the big definition, smooth manifolds, our main object of interest here in differential topology. And they're going to be defined in terms of these smooth structures that we've been discussing now for a bit. So a smooth manifold is a pair M, S, where M is a topological manifold and S is a smooth structure, meaning a maximal smooth atlas on that topological manifold. So a set of charts on M that covers M, which is also compatible, meaning that, which is also smooth, meaning that all chart transitions are smooth if they have non-empty domains. And in fact, this S is maximal, contains all such charts on M so that all these intersections that are non-empty are smooth. So that is what we define to be a smooth manifold. And what this allows us to do is actually distinguish between different types of smooth manifolds on the same topological manifold, but with different smooth structures. So for example, something that I will eventually be discussing is one of Milner's results, that there are spheres that don't have the same ordinary differential structure that I'm going to be introducing as an example soon. There's lots of spaces that we should get acquainted with, and the spheres, Sn, embedded in Rn plus 1, are definitely one of them. They're an important space to actually study. But one of the results of Milner is that the construction of the differential structure that I'm going to give you on Sn, it isn't unique in some dimensions. Particularly in S7, there exists what was coined at the time and is still called today the exotic 7 sphere. So I will hopefully eventually get to that. But for right now, that is the purpose of using smooth structures to define smooth manifolds. It allows us to distinguish between two different smooth manifolds based on which smooth structure they have. The problem with this definition is that I'm asking you, in order to write down a smooth manifold as this pair, I'm having to ask you for a smooth structure. And as we discussed, a smooth structure is the set of all charts which is compatible with some given smooth atlas. So that's very, very hard to construct in general. It's very, very difficult to write down one of these smooth structures. And so what we do instead is we recognize that the smooth structure generated by any atlas contained in S is always going to be S. So it will, in a sense, still be the same manifold. We'll just be looking at it with less charts. But it doesn't really matter which choice of charts we use because they're all compatible with our smooth atlas. So instead of using our smooth structure, our smooth structure, we use any old atlas A, which we like. It's small and nice and something that we can contend with potentially. And we say that this is in fact a smooth manifold and is equal to this smooth manifold if our smooth structure A is if our smooth atlas A is contained in our smooth structure S. So this will be the working convention. Even though we will all understand that when I'm talking about a smooth manifold, I'm actually referring to a particular smooth structure on it. When we're doing work and proof and examples, we'll always just be using a single smaller chart, especially if we're doing examples, because otherwise calculations would become intractable before we even wrote down the manifold. So this is the main object of study. If you don't know very much about topological manifolds, I would definitely look into them because we're going to be using the properties of topological manifolds and continuous functions on them quite heavily in the next part. Because now that we have this smooth manifold, what having a smooth manifold does, as opposed to having just a topological manifold, is it allows us to define the concept of smoothness on functions, maps between these manifolds. So that's what's going to be coming up next, a whole lot of theorems on the different smooth maps between manifolds, how to construct them, how do you know for a fact when they are smooth, and different smoothness tests. All right, so I hope you join me for that.